2. Okay, so this one we're going to go over capacitors, just making sure we really understand how does the capacitor charge up. So really quickly to make sure you're good, which side is negative? Is it going to be plate A or plate B? And hopefully straight away you thought, of course, it's going to be A that is the negative side. So it could be A that is my negative side. So to talk through that, what happens is we know the longer side of the cell is the positive terminal, the shorter side is negative. How I remember that is a negative's got less lines or less lines in it, so that's the shorter side. Positive's got more lines in it, so it's the longer side, okay? So what happens is when I close this switch, we know that we've got these electrons inside this conductor, okay? So when we close this switch, we apply a potential difference, right? We know the purpose of the cell is to provide energy per unit charge, right? We know this equation, E equals VQ. So the potential difference is energy per unit charge. So the point of this cell, maybe it's a 6-volt cell, the point of this cell is to provide 6 joules of energy per unit charge, okay? So this provides the energy per unit charge, and then what happens is they move around the circuit. Now, I hope you're thinking, initially there's no charges on these plates. So what does that actually mean? We're not saying there's no charges. We're saying that overall the charges are balanced. So to show you, these plates are metals. You know that metals, way back from your GCSEs, we know the metallic structures have these positive ions and you have these delocalized electrons or these free electrons. So if I've got four positive ions, I have 4 negative electrons. So you can say like overall it's neutral, 0 charge. So what we're saying on these plates is we do have positives and negatives, right? But it's neutral. So that's why we can say overall there's no charges on the plates. But what happens is when we close the switch, the electrons move from the negative terminal around and get pushed on. So we're pushing these negative electrons onto this plate. So you think what we're doing on this side is we're adding more negative electrons. And you could think if you added loads of negative electrons, you know what's going to happen is this side becomes more negative. So that's why instead of writing all the positive and negatives, we can just write that it becomes more negative. Whereas this side is the opposite. This side is that the negative electrons are getting attracted round to that positive terminal. So what happens is we're removing electrons from that plate. So you can see as we remove electrons from the plate, that plate becomes more positive. That's why we can write that that plate then becomes positive. And what happens is these electrons keep getting pushed onto this plate and they get getting repelled away from this plate until the potential difference between the plates, so the potential difference between the plates is equal to the source, which is 6 volts. And the resistor is there just to slow down the charging, right? Because if there's no resistor, that would happen super fast, right? We might not be able to take any data. So normally what we do is we normally have an ammeter in the circuit as well, so we can see how the current changes over time. Okay, so again, what I want to see is how does the current change over time, okay? The current is really high at the start because it's really easy to push those electrons on, so high at the start. But over time, it gets harder and harder to push more negative electrons on to a negative plate. You can see if I'm trying to push a negative electron onto a negative plate, it's going to try to repel it. So over time, it gets harder and harder to push more electrons on, so the current drops over time. But if you didn't have a resistor there, that drop would be so quick, you could barely measure it. You could barely get any readings for current. So we put resistor in there to slow down the charging of the capacitor so we can take readings of current over time.